All right, greetings. Welcome to today's class. So we were looking at longitudinal dynamics. We saw how to calculate the ideal brake force distribution, and then we also did an analysis of wheel lockup. Like we got the vehicle deceleration at which either the front wheels or the rear wheels would lock, and then we saw how to interpret those equations. Then we started off with a brief discussion of anti-lock brake systems, right? So we looked at what were the functional requirements of an ABS. So as the name indicates, it's an anti-lock brake system, right? So it prevents the wheels from locking, when they are being braked. And when is the wheel set to be locked? A wheel is set to be locked if it stops rotating while the vehicle is still in motion. Okay, so that's when a wheel is set to be locked. And we then also looked at what are the performance requirements of an ABS. We need to ensure that the vehicle stability and steerability are retained during braking. An ABS should also adopt quickly to changes in the tire road friction levels. Typically we test for what is called as a transition mu state when there is a change in the friction levels at the tire road interface. And when we have what is called as a split mu surface or a split coefficient road surface, the ABS should also ensure that the vehicle doesn't yaw out of control, right? So, and finally, if ABS malfunctions, we should still ensure that the underlying standard brake system performs normally. Okay, so those are some requirements from ABS. We also looked at a very practical analogy, right, of stepping on a puddle of water and essentially, losing stability because of reduced friction levels or reduced traction levels at the interface between the feet and the ground, right? So we looked at all those aspects. So in today's class, let's start off with an understanding of these concepts by looking at what is called as a friction ellipse or the friction circle. Okay, so what is plotted here, right, in this particular diagram? So in this particular diagram, we are looking at the force capability at the tire road interface, and the vertical axis is the x-axis, is the longitudinal axis, and the abscissa or the horizontal axis has the is the lateral axis. So what we are plotting is essentially the limit of the longitudinal force on the ordinate and the limit of the lateral force at the tire road interface on the abscissa. So let us say, this ellipse by default, what we have drawn corresponds to a nice dry tire road interface. Okay. So what happens, if you are the origin, that means that, the tire road interface, there is zero longitudinal force and zero lateral force. Suppose, let's say we want to cruise at a constant speed, right? What will happen? We may need to provide some baseline drive force through the powertrain so that my vehicle starts going at a constant speed by overcoming various loads, right? Like rolling resistance, aerodynamic drag, grade resistance if applicable, drawbar pull if applicable, and so on, right? So that's where we would be if we were to cruise at a constant speed. Now, let us say we are going at some speed and then we essentially apply some mild braking. Okay, so let's say we are inside this ellipse. Okay, we want this much of braking force at the tire road interface. We are fine. All right, and let us say we are going straight and then we essentially do some steering. Okay, and then we are demanding so much of force along the lateral direction to change the course of the vehicle. We are essentially still within the ellipse. We are okay. Now, let us say we do combined braking and steering so that we are taking a turn. We essentially want to do some mild braking while doing steering. So these are the two, along the two axes, we are demanding these forces. So consequently, the net force which is demanded at the tire road interface is the vector sum of these two forces, right? And our operating point will be somewhere here. So this will be sort of combined braking and steering, right? So and this is still within the ellipse. This is still within the capability of the tire road interface, so we are okay. So now, what happens, right? Let's say, like we enter a scenario where we are going straight and we slam the brake. Let's say a child runs in front of the car. We slam the brake and we want the maximum possible braking force, right, at the tire road interface. So the brake system is designed such that we reach this extreme point. Okay, so this is the boundary of the ellipse, represents the dynamic limits of the traction force, right, available at the tire road interface. So when the negative x-axis represents braking. Okay, so that's why we reach that limiting point there. Okay, so now let us say we want to avoid hitting the child, right? So we slam the brake, but at the same time we give a small steering input, right, which corresponds to this number or this value, and then we want to look at the resultant. Now, if we look at the resultant force, we can see that we are outside the ellipse. Okay, and this poses a problem. Why? Because we want to do emergency braking and let's say some maneuvering to avoid an accident. Our capability at the tire road interface has gone, or the requirement at the tire road interface has gone outside the capability of the tire road interface. That's a place where we may have an issue. Now, if this happens, what do we need to do? Right? So we are going to go into some instability. So what we can do is that like the driver has asked for some steering and also like maximum braking. So one option will be to essentially go from here to here. But then like if I go from here to the point of maximum braking, then I will lose all steering, right? So I will not be able to get steering at all. And practically better alternative would be to go from this point to this boundary point. Okay, so let's say we call this points as 1, 2, and 3. One option is to go from 1 to 2, right? Then we lose all steering. But on the other hand, if we go from 1 to 3, we lose some level of, we have to reduce the braking effort that we are commanding, but that's okay. Anyway, we would not have got so much braking effort, right? So we are anyway outside the friction limits. So, but then like we still retain steering. So this sorts of like explains a scenario where we may need this ABS system to perform even on a dry road, right? Under certain emergency scenarios. So ABS, typically people will motivate by looking at wet roads and so on, right? But even on dry roads, it's quite useful, right? Because what we are doing, the driver commands some force, but then like it's not sustainable at the tire road interface. So what happens is that like the ABS system will reduce the brake pressure so that the braking force which is requested by the brake system through the brake system is also like maintained within what is available at the tire road interface. Okay, so that is what will happen. All right, so I hope it is clear why ABS is required even on a dry road. Okay, there can be scenarios like this. Now the problem is accentuated when we go for wet roads. Suppose we have rain, like and the road has become wet. It's the same vehicle, same driver, but then the road has become wet. So what will happen is that the friction ellipse will shrink. So I'm just drawing a shrunk friction ellipse. Oh, sorry. So this is, let's say, due to a wet road. Okay, so this one is the friction ellipse on a dry road. Okay, now we have a problem, right? Because let us say we are going straight and due to some emergency, the driver slams the brake. The brake system has been sized to essentially command a force which corresponds to 0.2. But now the limit of the dynamic limit which is available at the tire road interface is at 0.4, right? Because the friction ellipse has shrunk. So if I do not take any action, I will get into some unforeseen circumstances or undesired vehicle response. So now what will the ABS do? It will now once again reduce the brake pressure so that we can go from 2 to 4. Okay, so that we maintain the stability of the vehicle. So this is once again achieved by reducing the brake pressure from the level commanded by the driver. So there are multiple important points that we need to note. See, ABS by itself is not an autonomous brake controller. It intervenes only when there is a chance of excessive wheel slip and resulting wheel lock. And it essentially prevents that same by reducing the brake pressure. Why does it reduce the commanded brake pressure? Because the driver is commanding a larger brake force than what is possible, like at the tire road interface. All right. So that is why, like the ABS reduces the brake pressure and tries to maintain stability. But it is not very simple. Okay. So if you look at the actual brake system, it won't smoothly go to 4. Okay. It will try to go to some other point here, by reducing the brake pressure too much. And then like it will try to oscillate a little bit beyond 4. And then like it will keep on oscillating around this region. Okay. It will be working around this region. So we'll look at that shortly. All right. So that's how the anti-lock brake system works. And that's the essentially spirit of ABS, right? So as we discussed, even the equivalent analogy of walking, right? Let's say I am talking to you and walking, and I see a puddle of water before me. What do? I sort of like step carefully on the puddle of water. So what am I doing when I step carefully on the puddle of water? I am reducing the effort which I am commanding at the interface between my foot and the ground through my joints and my muscles, right? So that's the equivalent of what happens in the anti-lock brake system also. Okay, so the anti-lock brake system intervenes only when there is a perceived wheel lock and excessive wheel slip, right? So, and it tries to ensure that, like it brings the braking pressures to regions where the wheel slip is manageable. Okay, so that is point number 1. Okay, what are other points that we need to look at from this particular graph, right? So, of course, this is a nice graph to draw. Like we essentially get the mu x and mu y or fx and fy limits, like on dry surface, wet surface, icy surface, snowy surface, and so on, right? But then there are multiple challenges, right? Who will give us the knowledge of these friction ellipse in real time? So what do I mean by this? So if I'm driving a vehicle, right, how do I know even what is the actual tire road condition at this instant? And correspondingly, what is the corresponding friction ellipse? And most importantly, where am I in this diagram? Right? So all those are challenges, right? So although this is a nice tool to explain the concept behind ABS, if you want to implement it from this perspective, it may become a little bit challenging. Okay, so then what is it that we do? Okay, so we do the following. Okay, so we are going to define equivalent measures or metrics that characterize this phenomena, and then like we will essentially try to regulate them. So we are going to define what is called as a V. Yes, please. Yeah. Any questions?
Sorry to yeah, sir. In this friction ellipse, sir, why lateral is not as big as the longitudinal? Like why it is not friction circle?
So it depends on some tire design, right? So that's why some people will call it as a friction circle. I have drawn it in general as friction ellipse. Okay. So in some tire designs, it may be in the form of ellipse, but very close to a circle. Okay. Yeah.
Okay, sir.
It depends on the tire construction. Yeah. Yeah.
So where this icy road will lie in here, it will be dry and wet, or it will be less than
no,
wet?
no. Icy road will be even smaller, right? It will shrink even to a smaller region. Okay. Yeah.
Thanks, sir.
So this will be maybe icy. That may be the smallest ellipse. Okay. Yeah.
So it means that we need to give minimum braking effort here, right?
Yes, yes, absolutely, right? That's why if you drive a car on an icy road, even if you touch the brake a little bit, right, the wheels may lock, correct? Yeah. That is because our hydraulic brake system, assuming that we are driving a car, right? The hydraulic brake system is designed to provide this much of braking force when the driver completely depresses the brake pedal, right?
Yeah.
On the other hand, let us say this limit corresponds to, let's say, 20% of the pedal displacement, right? And we are already outside the limit, dynamic limit that can be supported. So that is why the wheel locks, right, on an IC bus.
So when we press a brake, we feel a sensation in our legs, especially when ABS is activated.
Yes.
This
Yes.
is because of that harmonic motion you just described?
So yes, we are coming to that. Okay, so those are what are called ABS pulses or ABS pulsations. Okay, so we will come to that shortly. Okay, yeah.
Okay, sir. Thank you.
All right, so
Sir, the friction ellipse, like this force is on lateral and longitudinal. So this ellipse size also depends on the rate of application of inputs.
This ellipse depends on the tire design. Okay, it comes from that perspective. Okay, and the vehicle level design. Okay, yeah. So
Okay,
this is given once you essentially choose a particular tire design for a particular vehicle. All right, yeah.
Yes, sir. Like if I am applying brake gradually, longitudinal force maybe at maybe X it will lock. But if I'm applying very fast brake, even at less than X it will lock, no sir. Like maybe on rate of
Okay.
application.
Okay. So let me explain that. Okay. So this, to the best of my knowledge, is not directly related to the rate of application, but to the extent of application. So let us say you have 0 to 100% brake pedal displacement, right? So this 0.2 corresponds to 100% displacement. So you are talking about the rate at which brake is being applied, right? Is it not?
Yes.
Okay, whether
Yes.
you are slamming the brake pedal or you are gradually going to this 100% displacement does not matter, right? So whether you are slamming the brake pedal or it's gradually going to 2, what's going to happen is that like you will always get the same limiting braking force, right? However, what may change is the dynamic load. We have not come to that. Okay, yeah.
Okay.
See, what do I mean by that? Let's say you slam the brake, right? The deceleration profile will be different, right? Is it not? Okay. So you plot A versus T. Okay. So let us say this is gradual braking. And as opposed to slamming the brake, the final deceleration may be the same, right? But then the deceleration profile is different. So consequently, what will happen? The dynamic load transfer profile will be different. Okay. And the dynamic load transfer also affects this ellipse because typically people will plot it in terms of the friction coefficient, mu x and mu y. But then, like if you plot it in terms of the forces, Fx is going to be mu x times Fz. Okay, I'm writing in a very simplistic way, and Fy is going to be equal to mu y times Fz. Okay, so now what's going to happen? Let's say you put it as functions of time, right? So typically time is suppressed. So there is a big difference whether Fz t is in this manner or this profile, right? Correct. So that will matter. All right. Yeah.
Yes, sir. Thank you.
Okay. So this is an important point. There is a subtle difference between the rate of braking and the extent of braking. You want to go from 0 to 100% braking, let's say in 5 seconds, as opposed to, let's say, half a second. The steady state magnitude of the braking force will be the same, but then the way we get there will be different. Okay, the dynamics will be different. Okay. All right. Any other questions before we proceed? No. All right. So due to these challenges in knowing this friction ellipse, right, in real time, oops, what happened? So we use equivalent measures. And what is this equivalent measure that we use? Like we are going to look at what is called as wheel slip ratio, or some people will also call it as the longitudinal slip ratio. Okay, so that is an equivalent term which is used. All right. So what is this longitudinal slip ratio? Let us discuss this. Okay. So let us say we consider this vehicle which is moving from right to left on the screen, and let us say Vx is the longitudinal speed of the vehicle. Okay, and the wheel is rotating at an angular speed of, let's say, some omega. And what we are doing is that like we are applying a braking torque tau TB in this direction, and let us say W is, or Fz is the normal load acting on the wheel. Okay, so let me not call it as W, let me call it as Fz to be consistent, and Fx is the braking force or the longitudinal force that is generated at the tire rod interface. Okay, so what happens is that, like, when at the tire rod contact patch, there is both sticking and slipping happening, right? So we are not going to have pure rolling motion when we have a pneumatic tire. As a result, there is going to be what is called as a wheel slip ratio, which is defined as, which is indicated as lambda, and then like it is defined as Vx minus V naught divided by Vx. So what is this Vx? Vx is the vehicle longitudinal speed. Okay, so Vx is the vehicle longitudinal speed, and V naught is the circumferential speed of the wheel. Okay, so it's the wheel circumferential speed. So it is essentially R times omega. Okay, so where omega is the angular speed of the vehicle. Angular speed of the wheel, and R is the tire radius, right? So that's the wheel circumferential speed. So there's a difference between the two, and then like we normalize it with Vx, and then like we calculate this wheel slip ratio, okay, like what is called as lambda. And this is the formula by convention which is used during braking. We'll also look at an alternative definition of this wheel slip ratio when we are considering traction or acceleration. Okay, so this lambda during braking, when defined by this formula, is typically varying between 0 to 1. The value of 0 corresponds to a pure rolling motion. Okay, pure rolling motion means Vx is equal to V0, so obviously lambda becomes 0, right? And lambda equals 1 or 100% corresponds to a fully locked wheel. So what do we mean by fully locked wheel? V0 has become 0, but Vx is not equal to 0. So consequently, lambda becomes 1. In a purely rolling wheel, Vx is equal to V0. Okay, so the numerator becomes 0. Okay, so that's why lambda becomes 0. Okay, so these are the two extremes. Some people will call it in terms of percentage also. So they will say wheel slip ratio goes from 0 to 100% during braking. Okay, so this is how the wheel slip ratio is defined. Now, what is the impact of wheel slip ratio on the phenomena that we have been discussing? Okay, so let's look at this, right? And we define this so-called friction coefficient, mu x or mu, as fx by fz. Oops, sorry, I think something happened. 1 minute. I think screen sharing stopped. Let me start sharing once again. All right. Okay. Sorry about that. I think. Oops. Oh, everything went away. Oh. Okay. Let me write things once again. You know, like yeah, this was Vx, and where was I? This was lambda, and we saw that lambda goes from 0 to 1 for a during braking, right? Lambda equals 0 corresponds to a pure rolling wheel when Vx is equal to V0, and lambda equals 1 corresponds to a locked wheel when V0 becomes 0, but Vx is not 0. Okay, so that's what we have. And then like we call the normal load as Fz and this as Fx, and mu x is taken to be Fx by Fz. Okay, so amongst other things, this longitudinal friction coefficient, right, mu x, depends on the nature of the tire rod contact surface and also the slip ratio. So how does it depend on the slip ratio? So a typical curve looks like this. So this is the longitudinal friction coefficient. We can see that the curve reaches a maximum around in the initial part of the slip ratio region, maybe around 15 to 20% slip. And then like what happens is that like it falls off, right? So beyond this, you know, it falls off, and this is where we reached 100% slip. So what happens is that like when we go beyond this peak value, So let's say we call this as mu p. You remember we drew mu p and then like lambda p, right? So this is lambda, right? So beyond this peak region, when the state of the wheel goes beyond this peak region, like we enter the unstable region, because the wheel we can go to lock very fast, okay, while the driver is still trying to get more from the brake system, right, by pressing the brake pedal. So that's going to be an unstable scenario. So that's something which you want to avoid. Now, what are some other challenges? Although this is a very representative diagram, we see that this mu lambda curve. So this is what is called as a mu lambda curve. Okay. So this mu lambda curve depends also on the type of the surface, right? And we can see that the peak values keep on decreasing as we go from a dry surface to a wet surface to a snowy surface to an icy surface. That is point number one. And also the slip ratio at which we get the peak also changes. Let us say on a dry road, we get a peak value around 15 to 20% slip. On an icy road, we may get the peak values around like 3 to 6% slip. Like so, the peak values are also the slip ratio at which the peak values also are obtained reduces. Now, this brings certain interesting challenges to us, right? So we have essentially converted the problem of avoiding braking to a problem of regulating lambda. Can we regulate lambda around lambda peak? So if I'm able to essentially regulate this wheel slip ratio around the peak value or lambda p, where I get the peak value of the friction coefficient, I get multiple benefits, right? What are the multiple benefits? I ensure that I get the maximum possible braking force for the operating conditions under steady, and consequently I will get the maximum deceleration and the shortest possible stopping distance. That's point number one. And I will also ensure that my vehicle doesn't become unstable because I won't go to log. Okay. So in that way, like whenever the vehicle is tending towards log, so can we, like if the lambda value of the curve is going to be like this, can we essentially identify this, that this is happening, and bring it back to this region? Okay. So that's a question that we need to ask ourselves. Okay. So, but then there are other problems, right? So this can be posed as a control problem. That is where we want to essentially regulate lambda in this region. So it may not be around lambda p exactly, but in a, let's say, a region around this peak, lambda p, where we get the peak mu, right? So, but then there are other queries, other questions that come around, right? What is lambda p? What is the value of lambda p at every instant of time? That itself we don't know, right? So because as we told, lambda p can be around 15 to 20% on a dry road, right? It can go up to 3 to 6% on an icy road. So how do we know a priori when the vehicle is being braked, what is the actual tire road friction level, right? What is the tire road condition? How do we detect those things in an automated fashion, right? So that's a big challenge for us. Okay. Suppose, let's say we circumvent the challenge, right? So we also don't know what is the value of lambda at each and every instant of time. Why don't we know what is the value of lambda? Please note, lambda is V minus V naught or Vx minus V naught by Vx, right? Times 100, of course. So if we use wheel speed sensors, let's say we are able to get a measure of V naught. But then the question is, how do we get Vx to the fidelity which is required for ABS applications? Okay, so that is also a challenge. So see, suppose if we want to control something, right, we should know what is the value around which it has to be controlled, what is called as a reference value. And then we should also know what is the value at this instant of time so that I can take corrective action if required. Let me give an example. So let us say we want to control the temperature of air in our room using an air conditioner, right? We enter the room, we switch on the AC. Let us say we set the temperature as 25 degrees Celsius. So the 25 degrees Celsius is what is called as a reference value or the desired value, right? So you and I want the temperature to be that reference value. Now, when we come into the room, let's say the actual temperature is some 32 degrees Celsius. That is the actual value. We measure it using some temperature sensor. Then what do? We compare the reference value and the actual value, and then like we take corrective action by blowing in cold air, right? And progressively the temperature, the actual temperature reaches, and the air conditioner adjusts its output accordingly. Okay, so that's how the AC will work. Now let's consider the equivalent case here. So here we have to first figure out what is this reference value of lambda p, right, for a given condition. So this problem of regulating wheel slip is what is called wheel slip regulation. Okay, it's an interesting problem which forms the bedrock of many active safety systems. Okay, so but then we also do not know what is lambda p. Okay, that is an interesting problem once again. It is what is called reference slip identification. What is reference slip identification? It is exactly this problem. Okay, how do we find the value of lambda p at each and every instant of time? Then comes another problem on wheel slip estimation. Because if you want to control the wheel slip, let's say by some means we have figured out lambda p, right? But then I don't know what is the actual value of lambda at each and every instant of time, right? Then how do we then get the actual estimate the value of lambda and then like take corrective action, right, based on that. So the ABS problem has to do all these things. Okay, so from a conceptual level. Okay, so that's what makes this problem extremely challenging to do. And there are obviously multiple things which come into play also, right? Because why? The vehicle conditions also may vary, right? So that is also something which can basically play a role, right? And we can also have the road conditions varying about which we may not know a priori information, right? So these aspects, like make the problem very interesting to solve. Okay, so but I hope the overall concept of wheel slip regulation and its connection to ABS is clear through this discussion. Okay, any questions before we go further? No. We are going to come to ABS pulsation shortly. Okay, in a few minutes we will come there, right? So I'm going from concept to realization, right? So this is the concept. The question is, how do we get the realization in practice? That's something which I'm going to discuss shortly. But before we go there, any questions on what has been discussed?
So this wheel slip regulations, is it some standard for industry-wise, or is it depend upon vehicle to vehicle?
See, the overall concept is wheel slip regulation, right? Ultimately, that's the phenomena we are doing, right? So if you ask me whether there is a standard process for wheel slip regulation, every company will devise its own method, right? That's where the technology lies, right? Is it not? Yes. But the core idea is wheel slip regulation. Like the core science is we are trying to achieve wheel slip regulation. Okay. Yeah.
Oh, okay, sir.
All right. Okay. Let's go ahead. So, okay, before we go ahead and see how it is realized, so I'm sure this is something which all of us would be familiar with. So let's say we take a passenger car and let's say the front wheels lock. Typically, the front wheels are the ones which are steered, right? So we lose steerability, okay? Because when front wheels lock, we essentially lose the ability to generate lateral forces of the front wheels. And consequently, even though we may rotate the steering wheel and the front wheels will physically rotate, right? But then the heading of the vehicle will not change. I'm sure you would have seen some videos and photographs where the steering wheel will be pointing in one direction, but the vehicle will be heading in another direction, right? That's because the tire rod interface has lost its ability to generate sufficient lateral forces, okay, due to this wheel lock. And if the rear wheels lock, what's going to happen is that we are going to have a more serious case. Both cases are serious, but this is more so. Why? Because we lose what is called directional stability. So what is loss of directional stability? Like we essentially, if what to say, perturbation is given in the lateral direction, it is significant. The vehicle can spin out of control. Okay, so this is more dangerous. So that's why we want to avoid rear wheel lock at any cost. Okay, so ultimately, if you ask me, wheel lock in both the front wheels and the rear wheels should be avoided. But if you ask, okay, you can prevent wheel lock in only one wheel, which one will you choose? I will always choose the rear wheel to be always, it should be ensured that the rear wheels never lock. Okay, once again, let me set the context. Ideally, both wheels should never lock. Okay, that is the ideal scenario. We should strive towards it. But we are given a choice. We have to choose that under a certain scenario. Like either the front wheels lock or the rear wheels lock. Which one would you prefer? I would say, okay, although front wheel locking is bad, let's go ahead with it. Okay, so that's what we will do. All right. So we will go with that, and consequently, what we do is that, like, we essentially ensure that rear wheel locking doesn't happen, so that, like, the directional stability of the vehicle is not lost. Okay, so that's something we tend to ensure. And if we consider articulated vehicle, okay, so in an articulated vehicle, this is what is called as a tractor, and this is the semi-trailer or the trailer. So if we essentially if we lock the front wheels of the tractor, once again, we lose steerability. Okay, so because by and large, the front wheels are steered. Okay, if the rear wheels of the tractor lock, we get into a very dangerous scenario, which is what is called jackknifing, where the tractor spins about the hitch point, and then the entire vehicle seems to fold, okay, and flip over. Okay, so that's what is called jackknifing. When the rear wheels of the trailer lock, we get what is called trailer swing. Okay, so this is also bad. Of course, the trailer will swing into the next lane, and it's going to damage other vehicles which are going to come in the adjoining lanes, right? So all the three should be prevented. But once again, this is the most critical. Okay, so this is why many standards will require that even if we go for limited ABS implementation, okay, we want to ensure that we have the ABS ensuring that the rear wheel lock doesn't happen. Okay, so that's something which we need to be very careful about. All right. Okay, so that's what happens in single unit and articulated vehicles. And all of us, I'm sure, will be aware of this. Like, these are generic items which go into an ABS. Like, we have wheel speed sensors, we have an ECU which processes all the data, and then, like, we have modulator valves which essentially pulse the ABS. We are going to come there, and of course, we are going to have the electrical circuit which essentially interfaces all these units. So now let's look at ABS pulsation, right? So I think one of us raised this point, right? So when ABS acts, we seem to get some tactile feedback at the brake pedal, right? As if there are some vibrations, right? What is going to happen? So if you look at a typical ABS modulator, so for the time being, let me consider a hydraulic modulator, which is used in a hydraulic brake system of a car. So there are three modes in it, right? So one is what is called as an open mode, another is what is called as a hold mode, and one is what is called a release mode. So let us say we take a typical hydraulic brake system, and let us say we have a master cylinder in which the fluid is pressurized, and it is given to the wheels. Okay, so where we may either have a wheel cylinder or a caliper. Okay, wheel cylinder is present in a drum brake, caliper is present in a disc brake. So this is the hydraulic link. So what happens is that we place the hydraulic modulator in between. So the hydraulic modulator can be in these three modes: open mode, when it permits normal operation, it doesn't intervene; hold mode, when essentially it isolates the brake from the master cylinder and maintains the pressure; and release mode, when it essentially reduces the pressure from the field cylinder or the caliper, right? So those are the three modes. So now let's look at an interesting diagram which sorts of like explains qualitatively how this ABS works and also the reason behind the pulses. So in this curve, what we have plotted is the following. So this is the longitudinal vehicle speed, and let's say this is the circumferential wheel speed, okay, Vx and V0, okay. So now what happens is that, like, we start from zero, we essentially start applying the brake, okay. So what happens at this curve, the top one is the curve which essentially denotes the brake pressure in the master cylinder. And this curve is the brake pressure in the wheel cylinder or the caliper. So what happens is the following. So till this point, we can see that the brake pressure is increasing and the wheels are slipping. And let's say at this point one, like the gap between Vx and V0 is perceived to have increased beyond a certain threshold, right? Then what we do is that, like, we can't keep on increasing the wheel cylinder pressure. So we go into what is called as a hold mode. So when we go to the hold mode, we can see that although the master cylinder pressure is still increasing, so we essentially sort of like flatten the wheel cylinder pressure. So we disconnect the connection between the master cylinder and the wheel cylinder or the caliper. So this is the master cylinder. I'm just redrawing the same diagram. So this is our wheel cylinder or our caliper, right? And this is the hydraulic modulator in between. So when the difference between Vx and V0 is perceived to exceed a certain threshold, we go from open to hold mode, right? Then what we do is that, like, we observe, and then, like, at point 2, we can see that the gap is further increased because the brake pressure which is commanded and the tire rod interface force, don't match. So consequently, we are demanding more braking force than what is sustainable at the tire rod interface. That is why Vx and V0, the gap is increasing. So what happens is that the ABS goes into the release mode. Okay, so we can see that the caliper pressure or the wheel cylinder pressure is then released. So consequently, what happens is that the braking pressure is reduced, and as a result, the wheel starts spinning faster. So when the wheel starts spinning faster, we can see that the gap between Vx and V0 reduces, and my lambda comes closer to the peak region. So then when essentially the gap between Vx and V0 has decreased beyond a certain limit, we once again go to a hold mode, and when there is sufficient potential for increasing the brake force, we once again increase the pressure, and then, like, we keep on cycling through these various modes, right? Open, hold, release, hold, open, release, and so on, right? So this cycling of the modulator provides this pulses, okay? So in most hydraulic ABS, it's around, like, I think 5 to 6 pulses per second, frequency of around 5 to 6 hertz, okay? This provides these pulses, which essentially are felt as those vibrations of the brake pedal. So consequently, the modulator, the ABS modulator, pulses through these different phases of open, hold, release, and so on. And that results in the pressure being varied, within the wheel cylinder and the caliper. And that ensures that, if we go back to this diagram, that ensures that, we are essentially trying to stay within this region, okay, somewhere around the pulse. So if you look at the trace of the mu lambda curve, we will go something like this. We will try to come back. We will go here, and then, like, we'll keep on coming back. So we are going to sort of like operate in this region. Okay, so that's what is going to happen. Okay, so that is achieved by pulsing the ABS modulator through these various modes. Okay, through the 3 modes of open, hold, and release. Okay, so this is how the ABS works. Of course, I have only given you a very broad concept level understanding. How is it actually realized, and how is it how the finer details are programmed are also very interesting. Okay, so but I hope we got a perspective of various concepts, right? The capacity of the tire road interface, the brake system capacity, and why ABS works the way it does, right? Based on our understanding of the friction circle, the friction ellipse, and the mu lambda curve. All right. Okay. So, in fact, it becomes very interesting to study braking. That's why I started off with braking, because as we discussed, the brake system is the single most important safety system available in the vehicle, and consequently, we should ensure that it is able to brake the vehicle in a stable manner, and it is typically designed such that when the brake is fully pressed, we want to command the maximum possible deceleration, right? That's why we go to the limit of braking, limit of tire road interface, and that's why the chances of stability being lost during certain operations like combined braking and cornering, or even straight line braking on a low friction surface, become very important, and we need to have active safety systems like ABS to help us, okay, under those emergency situations. Okay, so this is what I wanted to share as far as ABS is concerned. Any questions? Okay, so if there are no questions, we will close the session here today. From the next class, I would start off with drive or traction, and then we will look at the same problem, or I won't say same problem, the problem of longitudinal dynamics when the vehicle is being driven. Okay, we have looked at the problem of longitudinal dynamics of a vehicle when the vehicle is being braked. So now we will look at the opposite problem when we see what happens when the vehicle is driven. All right, so that's something we will start in the next class. All right, okay. So if there are no questions, let me close today's session here, and we will continue in the next class. Okay, so let me stop the recording. Thank you.